Thank you for that introduction. And hello, and welcome to this Dynaflow webinar on avoiding surge pressure failures due to waterhammer and enclosed vapor pockets. So today what we're going to cover is, first of all, what is waterhammer or surge? Then we're going to look at how can gas pockets worsen that effect. And then based on the project experience of DRG, we're going to look at a series of example cases. We're then going to conclude with a series of tips for good design before closing the presentation. So what is surge? Here we're considering surge as a high pressure wave due to a sudden transient event. For example, the rapid closure of a valve. What you see here on the left, you see a valve. As the valve is closed, you're rapidly stopping the approaching fluid column. If we close the valve and stop the fluid column, then we generate a pressure wave which travels back through the system. The maximum possible amplitude of this pressure wave, if it's closed instantly, is the Joukowsky peak. And that is equal to the fluid density times the velocity times the speed of sound of the fluid. So if we consider the case for water system, we've got a fluid density of around 1,000 kilograms per cubic meter, with a flow velocity of around 1 meter per second, and a speed of sound of around 1,000 meters per second. That leads to a maximum possible amplitude, if we've got instantaneous closure of the valve, of around 10 bar. Now, what problems can waterhammer lead to in your piping? Well, first case is an excessive pressure can lead to rupture. What you see on the left is failure of the longitudinal weld in a piping system due to excessive pressure. But the passage of the pressure wave can also lead to net forces on the piping, which can lead to bending stresses. For example, what you see on the right hand side, we see the surge peak at one of the elbows in an elbow pair. During steady state operation, the pressures will be balanced if we discount the effects of friction, which will mean there's no net force on this between the two elbows. However, when the pressure wave, denoted by the red triangle, is present at one of the bends, in this case the right hand bend, then there will be a net force. The pressure will be higher at P2, which will lead to a net force which will pull the piping as shown on the lower image on the right. This net force on the piping will lead to deformation of the piping and bending stresses in the bends. If there was an axial stop included, the piping would not necessarily bend, but then there will be a large force on the axial stop located between the axial between the bends. And this limit stop may not have been designed for such a large force. The severity of the waterhammer effect can be increased if a mechanical eigenmode is excited. The passage of the surge wave has a characteristic frequency, and that is dependent on the system length, so the time it takes for the surge wave, if it reflects from the other end of the system, to pass back and then reflect from the closed valve back and forth until it's damped out by friction. This is based on the length of the system and also the speed of sound. If the frequency of the surge wave, the passing frequency of the surge wave, corresponds with a mechanical eigenmode, then that mechanical eigenmode, for example, the middle of the three on the right hand side, will be excited, and then the effect of the surge wave will be larger than it would be had the mechanical eigenmode not be excited. And this multiplication, depending on the dampening, can be up to a factor of 10. If the mechanical mode is not excited, for example that on the left, then this response will be much lower for the same surge amplitude. Now we've considered the case upstream of the valve. Let's now consider the case downstream of the valve. Here we see the fluid moving away from an open valve, which is then closed in image 2. Because the fluid has momentum, the fluid continues to move downstream, and that means a low pressure region forms immediately downstream of the valve. The pressure in this region drops, and depending on the operating pressure of the system and the momentum of the fluid, the pressure can drop to the vapor pressure of the fluid. That means dropping to the vapor pressure, there's portion of the fluid will cavitate to form gas bubbles. The fluid that was moving downstream will also now change direction, because now the pressure downstream of the valve is lower than the pressure further downstream, and the fluid will return towards the valve. The fluid will then be stopped as it cannot pass through the valve, and this will lead to a pressure rise as the cavity bubbles are imploded as the pressure rises. Let's now look at a video of cavitation downstream of a valve. This video has been taken by the Fraunhofer Institute in Germany and shows the cavity that forms downstream of a valve closing very quickly. The valve is located immediately to the right of the image, and the flow is moving from right to left. And what you'll see as we view the video is that cavity forms immediately downstream. This will then be imploded as the fluid column returns, and then will grow again as the fluid column moves back downstream, and then will then implode again as the fluid column returns. Okay, so let's review that again. So what you'll see a very loud noise denoting the valve is closed. See the cavity forming on the top, and the fluid moves back and forth, and the cavity is damped. Okay, so now moving on, how can gas pockets worsen this effect? Well, first of all, how can a gas pocket occur? We've got a liquid system. Well, firstly, air can accumulate in a line, typically for two reasons. First, we can have an elevated section. So if air bubbles in the fluid move to an elevated section, they can tend to accumulate. For example, here we're showing you a picture of a bridge over a road with a process line. And if this section is not vented, then the air bubbles will accumulate with time in this elevated section and can, in a severe case, fill the entire line. When a line is out of use, there's a possibility that there's a small leakage. For example, in this case, there's a leakage of a check valve. Then air can be drawn into a system. So, for example, this was a case on a platform. This is the water system, and then moving at a higher elevation, which is drainage of this line, was a small 2-inch potable water system. And what happened is there was a large diameter check valve downstream of the pump. So when the pump tripped, the check valve closed. However, the check valve had a small leakage, and because the potable water system at the highest elevation, this system drained first, and air was drawn in at the top of the system. And by the time the pump was switched on again, a large proportion of this line became filled with air. So why is that gas pocket such a problem? Well, it leads to fluid velocities that can be larger than during steady state operation. For example, the case on the left, what we're showing is a liquid column is entering a system which is partially full with gas. And what you see is the system pressure is higher than atmospheric pressure. System pressure will typically be the discharge pressure from a pump. The gas has typically entered into the system through a small leakage, for example, in a valve. The fluid column will accelerate into the gas based on the difference between the system pressure and the atmospheric pressure. So look at Bernoulli to give us the velocity of the fluid. So this will be typically much higher than during steady state operation. However, when this liquid column reaches the point of the leak, the fluid column will be stopped abruptly, as the fluid column cannot pass through the small leakage in the same way the gas could. And this will lead to a large waterhammer peak. For example, it could easily be that the liquid column will be travelling 10 times faster than during steady state operation. Okay, let's now, based on DRG's project experience, review a series of cases to illustrate these effects. Here we're going to consider the case 5 different failures. We'll look at the case of a rapid filling of a line. Secondly, we're going to look at the sudden transient event, followed by the implosion of a gas pocket. and then cavity collapse with a pump trip, and then the effect of a liquid slug within a gas line. Case 1. Rapid filling of a line. This considers the case of a jetty firewater system where a deluge valve is quickly open. The line had been out of use, and that had meant that the line had largely come to be filled with air at atmospheric conditions. When the pump was switched on and the deluge valve opened in the order of 1 second. And because the pressure at the discharge of the pump was much larger than that of the gas within the line, the fluid entered the firewater system with a very high velocity of around 10 meters per second. When it reached the end of the system, the fluid column was stopped and Joukowsky peak passed back through the system, leading to large unbalanced forces on the piping. And what we're going to show you here is a series of failures that occurred during this filling case. On the left-hand side, we'll see the axial movement of the piping. You see from the upper image on the left, you see that the rest support, highlighted, has fallen from the concrete base, okay, due to a large net force in the right direction. The lower left side shows you two line stops. So you see that line stop has not moved. However, the friction between the buckle and the pipe is insufficient to restrain the piping, and the piping has moved through, as can be seen by the scratch marks which indicate the previous position of the buckle. On the right hand side, you can see the failure of a coupling due to the net force that's applied to the bent, which has pulled the elbow out of the coupling which connects it to the axial section of the piping. You can also see the same effect on a transportation line. This is a transportation line that was being filled for a hydro test. What's happened is the line was full with air at atmospheric conditions. The valve between the water pump and the line was opened, and the water, moved very quickly into the transportation line. When it reached the end of the transportation line, as only a portion was being hydro tested, there was a large net force at the end of the system as the fluid column was brought to rest and the Joukowsky peak was formed. This net force pulled the line much like you would pull an elastic band and caused the ripples in the line that you see in this photo. Case 2 is that of a sudden transient event. Here what you see is, on the left you'll see a rest support that has been pulled from the I-beam upon which it was resting. And this happened because of a sudden leak near a flange. Because of the leakage, there was a rapid drop in the downstream pressure, and this pressure drop was communicated back through the system as a pressure wave, as a surge wave that travelled through the system, leading to pressure differences between the elbow pairs, which resulted in large forces in the pipe axial direction. As well as pulling rest supports from their I-beam below them, it also resulted in excess loading on the axial stops. As can be seen in these two images, the I-beams were not designed for the pressure but the unbalanced forces caused by this type of surge scenario, as the axial stop has communicated a large axial force onto the top of the I-beam, which has introduced a torsional moment and has led to failure or plastic deformation of the I-beam, shown on the left, and you can also see on the right-hand image. To give you an indication of how quickly these surge loads occur, we can show you this final image for this case. And you see here that the support is clearly not central over the I-beam and has moved to the left in this image. This is a rest support, by the way. Next to it, for one reason or another, a series of washers, a stack of washers had been left next to the rest support. You see that these washers, though, have not moved, even though a very abrupt transient scenario has occurred, indicating that the pipe support has moved very smoothly across the pipe and has not caused vibrations. Moved very quickly, has not caused vibrations in the beam upon which it is supported. In the third case, we're going to consider the case of implosion of a gas pocket downstream of a pump. The gas pocket formed in a blinded T on the discharge side of a pump. When the pump was tripped, the fluid moved away from the pump and then returned. The returning surge wave had a pressure that was in excess of the pressure of the gas pocket in the blinded T, and that meant the fluid accelerated into the gas pocket and was stopped at the end of the blinded T, led to a large pressure peak. The effect of this pressure peak was quite spectacular, given it was a fiberglass line, and this resulted in the blind flange being blown off the T and ended up 3 meters away from the line. Case 4, we're going to consider the case of a cavity collapse after a pump trip. This cavitation formed during an emergency shutdown of the pump. The pump was a vertical riser located 10 meters below the check valve. When the pump was tripped, the flow continued to move away from the check valve, which then closed, as there's no more flow passing through. The cavitation formed downstream of the check valve, given the low pressures in that region. And when the fluid returned, the cavitation imploded, and this led to large pressure peaks and unbalanced forces in the piping. With the following video, we can show you the effect of the implosion of this cavity. Okay, what you're seeing in this video is this is the valve. This is the flange connection shortly downstream of the cavity, and the cavity is located on the right-hand side of the image. So play the video, you'll see the pump shut down, and then you'll see a large force being applied to the piping and the vibrations that are associated with the collapse of the cavity. Okay, let's play that again. What you saw there very clearly was the vibrations, and that you could noticeably see the vibrations due to the collapse of the cavity and the pressure peak passing through the system. For our final case, we're going to consider the case of a liquid slug which has been trapped in a gas line. We'll start by showing you how dramatic the failure was. The gas line was around 4-inch diameter, and you see that the ball valve has been totally blown apart by the liquid slug impacting upon the ball valve. You see the ball of the valve is no longer present, and you see that the valve body has been blown apart. The ball was blown downstream and has never been found. But why did this happen? Well, what happened is the liquid slug had been trapped within the gas line. This was then taken through the gas line at the speed of the gas, which is around 10 meters per second. However, when it reached the valve, this ball valve in this case, the valve was only partially open. And although the gas flow could pass through without being restricted, the liquid slug could not pass through at the same speed and was brought to rest. In bringing it to rest, Joukowsky peak occurred, high pressure, but also a large net force was applied to the valve. Now, the amplitude of pressure depends on the gas volume between the liquid slug, and the valve. As the valve did not present a restriction to the gas flow could pass through the valve without a problem, and therefore did not give any cushioning effect to this liquid slug as it approached the valve. And therefore we ended around the maximum pressure peak that you could have on the right-hand side. Let's look at the effect of the liquid slug. We see this is the line upstream of the valve, and you can see on the left-hand side you see this plastic deformation in the hoop direction due to the increase in pressure as the liquid slug is brought to rest. On the right-hand side, you see that the axial force has caused the outlet side of the valve to be pushed downstream and has been bent, whereas previously it was a 45-degree connection, much like the other lines that you see next to it. So let's go and look at some tips for good design to try and avoid these problems. Well, good design practice, we need to think about can we accommodate the scenario through good mechanical design, or should we try and remove it in the process design or reduce the possibility as far as possible? If we have to accommodate it, how can we do that? And also, how can we stop the formation of gas pockets in the first place? So first we need to ask the question, do we need to design to accommodate the possible operating scenarios? For example, the opening and closing of a valve is an unavoidable operating scenario that we have to design for, and therefore the system should be designed to withstand these scenarios. An unexpected scenario, though, would be a failure due to trapped air that should have been vented. The process or the mechanical design needs to be such that these scenarios cannot occur. So how can we reduce the severity of transient scenarios, such as valve opening or pump shutdown or startup? Well, with valve closure, we can increase the valve closure duration, and this brings the fluid to a rest in a more controlled manner. However, sometimes with, for example, emergency shutdown valve, closing the valve more slowly is not an option. With starting up of the pump, we need to ensure the line is filled in a controlled manner, not merely switch the pump on and begin flowing into a line that is largely filled with air. An option would be to include a recycle loop, so that then a portion of the fluid would pass back through the pump and only a smaller amount would flow into the line, which would then mean that the fluid column does not travel at such a high speed. We could also adapt the system to accommodate the scenario. So for example, here we show the example of a cavity forming downstream of a check valve. To prevent the formation of this cavity, we could include a surge vessel. And with a surge vessel, when the pressure drops below vapor pressure, fluid from the surge vessel will travel into the main line and prevent the formation of cavities, because the pressure would not drop below the pressure in the surge vessel. And this will prevent the cavity peaks which could occur when the fluid reverses back and moves back towards the check valve. We could also look at changing the supporting configuration. For example, if we look at the following video, you'll see that the piping moves quite dramatically left to right. As say from the movement of the piping, we could easily stop the movement of the piping by including some additional restraining into this bend. However, the inclusion of additional restraint should always be done at the same time as considering the requirement to allow thermal expansion of the piping for steady load. Additionally, when considering additional supports, we should also consider that all parts of the support need to be sufficiently strong. For example, the example shown here, we see an axial stop, which has got 3 buckles, so remains on the line. However, the T-post is not as strong as the pipe shoe. And you see that T-post, much like those shown previously in case 2, has deformed, as it's not able to withstand the torsional moment generated by the surge load. If we want to limit the formation of gas pockets, then we should consider that low pressure lines, for example, if the pressure is just above atmospheric, low pressure lines with elevated sections can very often have cavities forming during transient events. For example, this is an example of the road bridge. Whilst with the dead ends without a vent, for example, that's shown in case 3, where the fiberglass T was totally failed, it will be much more beneficial in that case to have the T connection in the horizontal direction rather than the vertical direction, as then no gas pocket would be able to form, as the gas would not accumulate at the highest elevation. So let's just close with a few closing comments. So we said waterhammer arises due to an abrupt transient event, such as the closure of a valve or the tripping of a pump. And gas pockets can worsen that effect. For example, they can occur in elevated sections or when a system is left idle. In solving the problem, we can solve with mechanical changes, such as rerouting or supporting, or also process changes, such as surge vessel, vents, or controlled opening. And in presenting these cases and this presentation, we hope to give you an illustration of the severity of the failures that can occur if these scenarios are not considered sufficiently. Okay, well, thank you for listening to the presentation. And if you have any questions, we'll be happy to answer them now as part of the forum.